Hello everyone and welcome. And today I will be giving you a brief overview of our self-service PLECS model generator. To find the tool, head over to the Design tab found in the header anywhere on onsemi.com, and under Tools and Software, you'll find the self-service PLECS model generator. Before you begin, a MyOn account is required. However, once created, you will have full free access to the tool. To generate a model, go ahead and select Generate Model. On the first page, you'll find in the header the home page, which brings you back to this initial page, any previous requests that you may have made, a user guide, as well as an application note to enhance your knowledge of the tool, a link to our Elite Power Simulator where you can use these PLECS models, and a support link. First, you'll select your product type, and we support both discretes and modules. Today, we'll focus on a discrete device. For your product technology, we support FieldStop 7 IGBTs, as well as any one of our M1, M2, and M3 silicon carbide MOSFETs. We'll select our M3 device. For product voltage, this technology currently supports 1200 volts. And under product, you'll see the full list of our 1200 volt M3 silicon carbide MOSFETs. However, today we'll be focusing on a TO247 4-lead 22 milliohm 1200 volt M3S silicon carbide MOSFET. In the next tab under process condition, you have the ability to either select the nominal case, the worst case conduction loss, best case switching loss, or best case conduction loss, worst case switching loss. This is important for testing the edge cases of the lots that you might receive when you get your physical devices. And what you'll find in a data sheet is that there is some variation in the typical value that's listed for the devices. And that may be a slight variation in RDS on and breakdown voltage and threshold voltage and the capacitances of the device. And being able to optimize the model for those conditions will give you the best expectation of how your real design will perform. Today, we'll move forward with just the nominal case with typical values. For your switching type, you have the ability to either select a regular double pulse test simulated setup, and this is good for validating hard switching applications. However, for soft switching or partial soft switching applications, we have a unique topology that allows us to validate these models for, again, soft switching and partial soft switching cases as well. Today, we'll be focused just on a hard switching case. In your regular double pulse test setup, you have half bridge and quarter bridge configurations. And in a half bridge configuration, you'll opt for the same MOSFET on the high side. However, in a quarter bridge setup, you have the choice between either an ideal diode with zero capacitance or a silicon carbide diode. For the technology for your SiC diode, you can select either D1 or D3, as both of these families support 1200 volts, which we'll need to match the MOSFET. Lastly, under product, you'll select your diode, and we'll move forward with a 50 amp rated 1200 volt SiC diode. Under characteristics, this is where you can input the gate drive voltage for the switch. And for your VGS, we recommend -3 volts for the turn off and 18 volts for the turn on for our M3S silicon carbide MOSFETs. However, if you wish to test a different gate drive voltage, you can enter those values here. Under conduction characteristics, you can input the transistor current, and while these devices can operate in both the first and third quadrant, current can be positive or negative. And we'll vary these values from -50 amps to 50 amps in steps of 5. For the diode current, the device will be in forward conduction, so positive. Therefore, we'll start at 0 amps, increase to 50 in steps of 5. For our switching characteristics, we'll need our current to be some value above 0. So we'll start at 5 amps, increase to 50 in steps of 5. For our load voltages, you can either input your specific value that you're testing the devices in, or enter a number of load voltage conditions to build a more granular model. And in this case, we'll select 600 volts, 750 volts, and 900 volts to test at. You can add as many as you want simply by separating them by a space. Similarly, for the temperature value, you can input as many different temperatures that you want to build the model at. However, in this case, we'll just do 25 degrees, 75 degrees, 125 degrees, and maximum operating temperature of 175 degrees Celsius. And what you'll find is that this allows you to build a model that's much more accurate than a datasheet-based model, considering this is tested at all of these different conditions instead of just the few conditions that the datasheets are built off of. On the last page, you can see the switching circuit schematic featured here on the left in this quarter bridge configuration. And what you can now do is input 30 different parameters to build out this model for what your setup looks like. For the gate driver, you can enter values like the internal gate resistance or the rise and fall times. For your gate drive circuit, you have the interconnect inductances as well as your maximum and minimum values for your RG on and off. You have a few choices for damping, as you can either select the damping on the gate to source of the gate driver. You can select values for a snubber circuit across the device, or you can enter a parallel capacitance across the high side and low side device. For our load inductor parasitics, you have the resistance and the capacitance of that load inductor. For our device layout parasitics, you have both the high and low side resistance and inductance for our top and bottom device. You have your switching loop parasitics. You have your input filter parameters that can either represent things like if you have PCB leakage inductance or perhaps a filtering inductor, or a decoupling capacitor or a filtering capacitor and its corresponding inductance and resistance. And lastly, you have a current measurement measured through a shunt resistor that can either be placed on the source side of the low side FET, the drain side of the low side FET, or at the load. Once finished, go ahead and select Submit Request. And in a matter of minutes, your model will finish generating. Once your model is finished, you will see the status as done, and you can download the XML file for the PLECS model here. If there's any of these values that you wish to change, you can select the Recall button featured in the top right, and this will allow you to recall the model with all of these values that you entered and change anything that you may want to. You also have access to some plots in the tab next to Details that plot things like the switching losses versus the drain current versus your gate resistance, and so on and so forth at all of these different test conditions that we modeled. Under Request, you have access to all of your previous requests that you may have made, where you can see some basic information about the model, as well as access to, again, that XML file to download again or to recall the model. For more information on how to use this tool and others, as well as the latest updates of our onsemi portfolio, head over to onsemi.com. Thank you, and until next time.